Okay, good morning. So, let us start. So far until now you heard about how do we use spintronic principles for reading information in hard disk drives. So, from today onwards we will be learning about MRAM, how do we write information, how do we store information, what are the parameters that determine the readability of MRAM and things like that. Okay. So, today we will focus on the writing methods, how do we write information. Okay. So, you might think that magnetic random access memory is very new, okay, but it is one of the oldest random access memory. Okay. Even before the DRAMs, SRAMs were introduced, the computers used magnetic memory. Okay. So, DRAMs and MRAMs came in 1960s and later, okay, whereas in 1950s computers used magnetic memory. So, it is called magnetic core memory. So, these are tiny pieces of magnets. So, the information is stored here and you can see copper wires going through. So, these are like toroids. So, it is like a circle with a hole, it is a kind of ring, then you send wires. So, you use these wires to write and read information. Okay. But after, I mean these things are made using hand, you know. So, like people use people make sweaters. So, it is like making sweater. So, people use the toroidal rings and copper wires and make these memories using hand. Okay. So, kind of handicraft memory, but once we could make SRAM and DRAM by lithography, mass manufacturable, then this memory died. Okay. Now, after almost 50 years, now the magnetic random access memory is coming back. Okay. Like old Hindi movies of 1980s, the father gets killed by villain, then son comes out to take revenge, right. So, now the MRAM is coming up, probably to replace some of these villains. So, this is how the MRAM will look like. So, you have a transistor and you have this magnetic tunnel junction. Okay. So, in magnetism you will come across the words TMR and MTJ quite often. So, when you encounter the word TMR, it refers to tunneling magnetoresistance. So, basically this represents a phenomenon, right, physical phenomenon, whereas MTJ refers to magnetic tunnel junction. So, it represents a device. Okay. So, TMR represents a phenomenon, magnetic tunnel junction represents a device, and people of two different industries use different terminology. So, people in the hard disk industry, they use TMR sensors, okay. So, they call the sensors based on the phenomenon, because we have been using AMR sensor, GMR sensor. So, it is quite likely that they continued the tradition of TMR sensors for reading information. So, they call the sensor based on the phenomenon, whereas the MRAM community uses the word MTJ to represent the device that stores the information. So, here this MTJ can have high resistance or low resistance depending on the parallel or anti-parallel nature of magnetization in the two layers. So, they represent states 1 and 0. Okay. We are storing digital information. So, bits 0 and 1 are represented by having parallel magnetization or anti-parallel magnetization. So, like in the TMR sensor that we learnt, so we have one fixed layer. Okay, so this magnetization is always fixed to one direction, and the free layer direction is different. Okay. So, as I mentioned before, the fixed layer has many different terminologies. So, some people call it hard layer, some people call it a reference layer, fixed layer, pinned layer. So, all these terminologies mean the same thing. The layer whose magnetization does not change is called any of these layers. Okay. Then the magnetization of the second layer is varied as per requirement. So, today we are going to learn about writing, right. What do we mean by writing? What do we mean by writing? Huh? Pardon? Storing information, that is storing. Writing, I am talking about writing. So, you take your notebook, write using pen, right, that is writing. Storing means after you write using the pen, the information is stored. Okay. So, I am talking about writing. What do we mean by writing? Yeah. Okay, we have some format. What do I mean by writing? I have some information. What do I mean by writing?
Recording.
Recording. What does that mean?
So, in terms of magnetization, like we are magnetizing the material and that's how we are applying the magnetic field. So, that what we can say reference to this.
Okay, so we do some action to make these layers parallel or anti-parallel. Okay. So, if we apply magnetic field or do some other action to keep the magnetization of the two layers parallel, that is writing 0. Okay. So, if we take some action out of which these two magnetizations are anti-parallel, we are writing 1. So, writing 1 or 0 is magnetizing the free layer in one direction or the other direction. That is basically the writing. Okay. So, in magnetic recording, I told you, right, we have an electromagnet. So, we generate magnetic field. So, these electromagnets generate a magnetic field which keep the magnetization in one direction or the other direction, that is writing. Okay. So, in a similar sense, in magnetic random access memory, writing 0 means keeping the free layer magnetization parallel to the reference layer magnetization, that is writing 0. So, if you want to write 1, you switch the magnetization of the free layer to be anti-parallel to the fixed layer, that is writing 1. Okay, so, here if you notice, we have a transistor at the bottom, then MTJ is at the top. Okay, so, if you remember the first day of our lecture, I gave you the DRAM circuit, and in the DRAM the capacitor was somewhere here. So, this capacitor was used to store 0 and 1. So, in DRAM the capacitor is at the bottom of the transistor, but in MRAM you will notice that the MTJ is at the top of the transistor. Why? Why is it so? Okay, so if you take the DRAM of a semiconductor chip, the capacitor of a DRAM, what is this capacitor made of? Pardon? Dielectric. Okay. Yeah, you can say. So, this dielectric is part of the semiconductor manufacturing process. Okay. So, in semiconductor manufacturing process, you have silicon, you may dope with something, phosphorus or boron, and you may have some dielectrics. So, these are all part of the semiconductor manufacturing process, okay. So, which have been there for many years, almost for 50 years this process has been established. Okay. Suppose now you suddenly want to move to MRAM technology. So, in MRAM technology you have a copper wire here, then you have so many like antiferromagnetic materials, ferromagnetic materials. So, you are introducing so many new materials, okay. And later you will learn that after you make the MTJ, you will also do annealing at around 350 degrees Celsius and so on. Okay. Imagine you have this MTJ somewhere here and you do all these things, what will happen? What will happen? So, all these cobalt, manganese, they will go into the transistor element. So, you know the semiconductor chip is supposed to be very clean, you cannot have, it is a semiconductor material, right. So, you are controlling the doping very precisely. Okay. So, if you have all these elements and do annealing at 350 degrees Celsius, all these materials will go inside your semiconductor chip and your transistor won't function. Okay. So, we want to keep the semiconductor technology immune to everything else we do for MRAM. Okay. So, we do not want these things to be affected by whatever we do at the top. Okay. That is why we keep all the semiconductor related parts at the bottom. Then we have some copper, some metallic layers. Then we do all these things at the back end. So, it is called back end of the line processing, something like that. Okay. So, we do all the other operations like depositing the layers of MTJ, all those things we do after we finish all the transistor part. Okay. So, if you look at a memory array, it will look something like this, right. So, memory array you have word line and a bit line, and if you want to address some particular memory, so you send current through one row and another column. So, this particular thing will address this memory and things like that. So, MRAM also is very similar, except that now here we have that transistor and the MTJ, this thing is here. Okay. So, that is how we have MRAM. So, if you look at this picture, you can see that this whole thing is related to the transistor part. I am not very good in this semiconductor electronics, but these are all things related to the transistor part. Then on top we have this. Okay. So, these are the MTJs, magnetic tunnel junction. So, if I zoom in, it will look something like this. So, we may have the MGO here, free layer somewhere here and reference layer, all those things. Okay. So, this is the magnetic tunnel junction that stores the information. Okay. So, as we learnt before, I told you that I will keep repeating this triangle until the end of this course. So, whether you make a memory, I mean we are talking about some non-volatile memory or storage. So, when we talk about a non-volatile memory or storage, we should have some ability to store the information, retain the information, some ability to read the information, some ways to write the information. So, all these three criteria must be met. Okay. So, for example, if there is a water bucket, right, you write with your finger, you can write information, but water won't store information. So, writing alone is not enough, or if storing alone is not enough, you should be able to read also. All these three criteria must be met when you design a memory or storage element. Okay. So, today we will focus on the ways to write information. Okay, so like the semiconductor technology progressed following the Moore's law, the capacity of the chips doubled, I mean the number of transistors in a die kept doubling every year. Then somewhere in 2000 people realized that we cannot continue to grow in the Moore's law method, we have to rely on other alternative technologies. So, different communities started working on different topics. So, we have ferroelectric RAM, phase change RAM, STT, MRAM, field switching MRAM and things like that. Okay. So, ferroelectric random access materials use the materials like PGT kind of dielectric material. Phase change RAM uses the materials used in CD or DVD. Okay, so, these materials are amorphous. When you heat them and cool them rapidly, they will become amorphous. When you heat them and cool them slowly, they will be crystalline. Okay. So, this PC RAM has a high resistance in the amorphous phase and low resistance in the crystalline phase. Okay. So, you can store 1 and 0 using PC RAM. So, various communities, so people working on different materials, they were looking at alternative memories. Okay. So, the MRAM that we are going to learn today is competing with so many other candidates. For example, if you look at SRAM, SRAM occupies very large area. I will later explain what is F square, and SRAM also has a leak current. For example, SRAM is like a bucket where you keep adding water and water also leaks. Okay. So, if you want to store information in SRAM, you have to keep supplying energy. Okay. So, the energy required to keep the information in SRAM is quite high. And okay. So, every memory technology has some advantage or disadvantage. So, in that sense STT-MRAM has certain advantage and it has been implemented as a niche memory replacing something called E-flash. So, E-flash is some memory in your say digital watch or mobile phones where some programs are stored. Okay. So, when you start your phone or your watch, the program will be taken from this E-flash and run, things like that. Okay. So, there is some small memory different from SRAM or MRAM. This is another type of memory, non-volatile memory. Okay. So, this is where MRAM is currently being used, and we are looking at some other technology which may probably replace SRAM. These are the research work that is happening, and SRAM and DRAM are volatile memory. That means, if you switch off the power, they will lose their data, whereas MRAM is non-volatile. Okay, it will retain the power even if you switch off the power. Okay, so, there are some advantages because of which the industry have invested money and they are developing MRAMs, and they have achieved some success and they are in the path of making more products using MRAM. Okay, so, you can classify MRAMs into different types based on the writing methods or the way in which you store information and things like that. Okay. So, people give names like toggle MRAM to represent MRAM which uses certain way of writing. So, if you use a spin transfer torque for writing information, we have STT-MRAM and things like that. Okay. So, depending on how do we write information or how do we store information, there are many names for MRAM. today we will focus more on the writing methods. Okay, so at first we will learn about magnetic field assisted MRAM, then we will move to spin transfer torque MRAM. So, this is like chronologically, this was the early method of writing MRAM, and this is reasonably new. So, people have started studying writing information based on spin transfer torque somewhere around 2007 and later. Okay, so, this is even before 2000. You can say before 2005 or something like this. So, we will learn about some of the old technologies, then we will move to new technology and newer technologies. Okay, so, people often use the word switching to represent writing. Because as I mentioned, the reference layer is always in one direction. So, you switch the magnetization to be anti-parallel or parallel, thereby you write 1 or 0, right. So, basically you are switching the magnetization. So, that is why people use the word switching. So, switching basically means writing information. So, you write 1 or 0 by switching the magnetization direction. Okay, so let us start with the magnetic field assisted switching or writing mechanism. So, in this case we are using magnetic field. So, if you remember, in magnetic recording we are using magnetic field to write the information. So, we magnetize the materials to be pointing up or down, or to have magnetization left or right. Okay. So, we write bits by using electromagnet, which generates a magnetic field. So, in a similar way, in the field assisted MRAM, again we are using a magnetic field to write information. Okay. So, in magnetic recording we had a coil, then we have a ferromagnetic core. So, we use this core magnetic field to write information. So, if you remember the lecture on magnetism, I taught you 3 ways of producing magnetic field. Okay. So, in the first case I told you, if you send a current through a wire, you will produce magnetic field, not something like this. Then second one was solenoid, third one was solenoid with a ferromagnetic core. Okay. So, the third one is the one we use for magnetic recording. Okay. But for this field assisted MRAM, we are going to rely on this method. You have a wire, okay, you send current through the wire, then you produce a magnetic field. So, I told you that you can use your right hand to determine the direction. So, if this is the direction of your current, magnetic field is following the direction of your other 4 fingers. Okay. So, in this MRAM, a magnetic field is produced by current carrying wires, and we are using this magnetic field to switch the magnetization. Okay. So, look at the emphasis, it is not current carrying wire, I am using current carrying wires. Okay. So, there are more than one wires. Okay. So, there will be at least 2 wires. Okay. So, we have 2 wires and we produce 2 orthogonal magnetic fields. So, that means let us say one wire is coming towards you, this wire is producing magnetic field in this direction, say your anti-clockwise direction. Then we have another wire in the orthogonal direction, So, this wire is producing a magnetic field around this direction, okay, which is coming towards you going this way. Okay. So, we are producing two orthogonal fields to switch a particular MRAM. So, basically a particular MTJ element, magnetic tunnel junction. Okay. So, we will be sending current through the read line and bit line. So, if you remember the memory array I showed you a few minutes ago. So, we had a memory cell here. So, this memory cell is accessed by a certain word line, then certain bit line. Okay. So, in the case of this particular MRAM, we are sending current through two wires, one wire which belongs to the read line, another wire which belongs to the write line. Okay. So, we are using two wires to produce two magnetic fields. So, in this picture you can see we are sending current through one wire, it produces certain magnetic field. We are also sending current through another wire which produces another field. So, these two fields are orthogonal to each other, 90° with respect to each other. Okay. So, now I will show a brief animation to show how it works. Okay. So, in this picture you see two wires, one blue wire going this way, another blue wire going this way. So, the MTJ is somewhere here. Okay. Inside this there is an MTJ. So, you cannot see what is happening here. So, let me bring it out. Okay, MTJ has come out now. So, I have two layers, one magnetization is fixed, another one is free. Okay. So, when you send current through only one wire, you produce certain magnetic field. So, that magnetic field has rotated the magnetization direction from being parallel to somewhere this direction. Okay. Now, we send current through another wire. Okay. So, this current was making the magnetization to go in some other direction, but it could not switch. Okay. It did not become anti-parallel. Okay. So, we started with parallel magnetization. So, switching happens means it become anti-parallel. So, we are writing 1. Okay. So, by sending current through this wire or this wire alone, we could not switch the magnetization. We are only temporarily rotating the magnetization from one direction to the other, but after you remove the current, it goes back to the initial state. Okay. But when you apply both current, I mean current through both the wires, you can see the magnetization has reversed. Okay. So, the two magnetic field act together to switch the magnetization of the free layer. Okay. We use many terminologies. So, for this layer people use free layer, storage layer and so on. Okay. Okay, now watch again. One current does not change the final state. So, only by sending current through two wires we can switch the magnetization of a particular MTJ.
Storage device is in between the two wires.
Somewhere, I mean, now let us say you are viewing from the top. Okay. So, this one wire, then below this you have this MTJ, then this wire is at the bottom of. So, it is like top electrode, the other one is like bottom electrode, you can say. Yeah, this field is not enough to switch the fixed layer magnetization. Fixed layer has a, fixed layer is pinned with a antiferromagnetic material. So, you cannot change this easily. Yeah, the field is very low. Yes. Okay, the title of this slide is selective switching. So, what is the meaning of selective switching? So, why I use this word here? No, current direction, yes, of course, but why do I use the word selective switching? Pardon? You speak up.
So we are just changing the magnetic and elevation of the upper layer.
No, that one is not the reason why I use this.
In the array of many integers,
Hmm.
maybe we can select one particular which we want.
Yeah,
and
exactly.
leave the others.
Yes. So you have an array of, I mean, you have right line, bit line, right? So let's say we call this right line, and we call these bit lines. Okay, let's say you want to write information on the MTJ here. Okay, this MTJ is the one you want to target. Okay, so you want to make this say from 0 to 1. Okay, so you want to write information 1 here. Okay, so what you do? You send current through this wire B2, then you send current through this wire W3. Okay, so this whole wire B2 produces certain magnetic field. Okay, so throughout this wire, you will see the magnetic field going like this. Okay, so if this magnetic field is strong, it will write all the MTJs. Okay, so similarly, you send current through this wire, this will produce magnetic field throughout the length of this wire. So, if this magnetic field is strong, again it will write all the MTJs. Okay. So, what we are doing is we are sending a current lower than certain critical current, that any MTJ along this wire do not switch. Okay. The current in the word line or current in the bit line, sorry, is lower than critical current. Okay, so that the magnetic field produced by this wire does not switch any other MRAM. Okay, only the MRAM which is under the intersection of this IW and IB will switch. Okay. So, by choosing the two wires, we can selectively switch the MRAM cell we want to switch. Okay. So, that is the reason the word selective switching is used here. Okay. Yeah. Yes, the current carrying wires are traveling across the array. So, it is like yes. So, you have one wire going this way. So, one wire covers many MTJ. So, one wire in the right line or one wire in the bit line, they cover many MTJs. But the current we send is not enough to switch any MTJ. Okay. Current in any wire is not enough to switch any MTJ, but only when you have the two orthogonal fields, two orthogonal magnetic fields, you can switch the MTJ. Okay. So, this is the mechanism. So, what happens? What is the physics behind it? So, we will learn that now in the next few slides. Let us say this is the free layer of the MTJ. Okay. So, you know that because of shape anisotropy, we have one easy direction, we have a hard direction. Okay. This is the top view of the free layer is like this, the side view is something like this. Okay. So, in the absence of anything, the mineralization is pointing towards left. Okay, let us do the hysteresis loop of this particular piece alone. Let us forget about this one. Let us say we have deposited a free layer and let us do a hysteresis loop. Okay. So, we apply magnetic field along the easy direction. Okay. Sweep the magnetic field. So, we will get a hysteresis loop. It will look something like this. Then going back, so we will have the hysteresis loop looking like this. Okay. So, the coercivity is around say let us say 47 Oster. Okay. So, this is a normal hysteresis loop. Normal hysteresis loop, we just apply some magnetic field, we sweep some say minus 75 to plus 75, then we get this hysteresis loop with a coercivity of 47 Oster. So, this is the experiment number 1. Sweep H and measure, let us say magnetization or MR does not matter. Okay. The second experiment, what we are going to do is we are going to apply an external magnetic field along the hard direction. Okay. So, we call it H hard. Okay. We apply some magnetic field along the hard direction. So, let us call it with a suffix H hard. Okay. So, in the presence of this hard magnetic field, now we do the second experiment. Okay. Now, in the earlier experiment, the hard field was 0. Now, this hard magnetic field has some finite value. So, we sweep magnetic field again, we measure the MR. So, for example, if you look at this image, this curve sorry was measured when the external magnetic field. So, in this particular picture, for example, external magnetic field will be going towards the board. Okay. In the side view, this is the easy direction. So, you are applying transverse to the easy direction. In the top view, H hard is along this direction, H easy is along this or this direction. Top view is like this. In the side view, H easy is either along here or there, we are sweeping, and the hard magnetic field is always in one direction. Okay. These two are orthogonal direction. Okay. So, let us take this curve 40 Oster, we apply a magnetic field in the hard direction and its magnitude is 40 Oster. We are not sweeping this. Okay. This is fixed value, one value of H hard. We are only sweeping the magnetization in the easy direction, like what we normally do for measuring hysteresis loop. So, in this case, let me use another color. In this case, when I measure hysteresis loop, it looks like this. So, we see a hysteresis loop which looks something like this. So, what is the major difference you see now? Yeah. I mean, not all questions are tricky, some questions are very simple. So, feel free to answer without being scared. Okay, it is very obvious, right? Coercivity has reduced. Okay. So, when you measure the hysteresis loop of a sample with only one magnetic field sweeping, you have coercivity of 47 Oersted, but when you have magnetic field in the easy direction and hard direction, in the presence of two magnetic field, now the coercivity has reduced to something like 20 Oersted. Okay. So, that is what you see here. So, this is what we do in the selective switching. Okay. So, we are applying two orthogonal field, right. So, if you remember, we have a bit line, digit line, both of them are generating a magnetic field. Okay. So, we are using two magnetic field orthogonal to each other, which means the coercivity of the free layer here will be much lower than the coercivity of the all the other MRAM cells. So, what causes this reduction of coercivity? Okay. So, we learned that two magnetic fields produce lower coercivity. So, what causes that? So, that is explained in this picture. So, we will come back to the energy landscape again. So, when we talk about energy landscape, we are plotting energy as a function of the magnetization angle. Okay. So, for example, 0 means magnetization is pointing in one direction, pi or 180 means magnetization has switched by an angle of 180 degree. Okay. So, these two are the two easy directions. Okay. So, in the absence of any magnetic field, so we learnt that the Stoner-Wohlforth particles will have two energy minima, right. So, magnetization pointing in one of the two easy directions. And we also learned that these two states are separated by an energy barrier E b. So, do anyone remember what is the value of E b? So, what is this E b equal to? K u v. Okay. So, K u is the anisotropy of the material, V is the volume of the grain. So, in this case we are doing lithography. So, we can say the volume of the island. So, here volume is actually the volume of the free layer. Okay. So, the free layer and the reference layer are separate magnetic entities. So, here we are talking about the volume of the free layer. Okay. So, the free layer has material has certain anisotropy constant, you multiply the volume of the free layer. So, let us say the diameter of this is like 60 nanometer, then let us say this layer has a thickness of 3 nanometer. So, you can calculate the volume of this particular cylinder. So, that volume multiplied by the K u is the E b. Okay. So, when you apply no magnetic field, this is the energy landscape. Let us say this is your free layer viewed from top, let us say the magnetization is pointing in this direction, cross section. Okay, I am not drawing cylinder, I am drawing a cuboid. Okay. So, side view is like this. Okay, the magnetization of this particular the free layer is pointing like this. So, right now it is okay, let me change the direction. to be consistent with that picture, let me use this. Okay, so, this is your initial state. So, we are here. Now, let us say we apply a magnetic field. Okay, so, this is the easy direction. This is a hard direction. Let us say we apply a magnetic field along the easy direction, the opposite to its magnetization. So, in the absence of magnetic field, this was very low energy, but once you apply an opposite magnetic field, the energy landscape changes like this. So, now H E Z is not 0, so it has some particular value. So, it changes the landscape like this. Okay. So, you can notice that this state is becoming more unstable. Okay. But this field is not enough to totally switch. So, in magnetic recording, we apply this magnetic field value very large, so that this goes all the way here. So, our easy field was even higher. So, the magnetization cannot stay here, it will switch to the other direction. Okay, that is what we did in magnetic recording, but here we are not doing that. So, here we are applying a field in the easy direction, not high enough. Okay. So, it is just enough to reduce this energy barrier. So, you see now the energy barrier is reduced to a lower value. So, here the energy barrier is so high. So, when you apply the certain magnetic field, now the energy barrier is reduced. Okay, this is one scenario. We are applying magnetic field only along the easy direction. Now, let us do another experiment. I use another color. Now, we are applying magnetic field in the hard direction. Only in the hard direction, okay? No field in the easy direction. So, if I apply magnetic field only in the hard direction, that changes the energy barrier landscape like this. Okay. So, again applying magnetic field in the hard direction has reduced the energy barrier to certain height, lower height. Okay. So, you see this height is lower than this. Now, if you apply both together, okay, so there is a easy direction magnetic field and hard direction magnetic field. So, what happens? The hard direction reduces this energy barrier height, and the application of the magnetic field in the easy direction changes the energy landscape further. So, these two together will bring out this scenario, where this is no longer stable, this is the stable. So, the magnetization will switch to the opposite direction. Okay, so, why the applied magnetic field changes the energy barrier? So, you can understand based on these equations, okay, but I do not spend time on equation, but this is the concept. Okay. So, by sending current through two orthogonal wires, you change the energy barrier landscape from this to this, so that that particular cell switches magnetization. All the other cells, for example, the MRAM cells in the easy direction, I mean we are sending current through two wires, right. So, all the MRAM cells in this particular are having energy barrier like this, they do not switch, and all the other cells in this particular, for example, this MRAM, they undergo energy landscapes change like this, they also do not switch. Only this particular MRAM which is at the intersection have this energy landscape. So, only this can switch. Okay, so that is the field assisted MRAM. So, people can do, so what people do is like when they create memory array, they send certain current through the digit line, certain current through the bit line. So, bit line, word line, read. So, you can send current through two orthogonal wires. So, when this current is low, nothing happens, or when this current is low also nothing happen. But if these two values are of certain magnitude, for example, this digit line has certain value and bit line has certain value, this particular MRAM will switch. Okay. So, any current higher than this will definitely make the MRAM switch, but if you apply a digit current lower than this, it will not switch. Okay. So, only in this region the MRAMs can switch. So, these are the operating regions. Yes. So, the two wires in the orthogonal direction, they are providing the easy field and hard field. Yes, correct. Okay, so I gave you one explanation of how this whole thing works. There is also another explanation, but I think we can skip this today. Okay, so this I told you that this switching technique was used until say 2006, but after this people dropped this and moved on to spin transfer torque MRAM because of certain limitations. Okay. So, the first limitation is that this technology is not scalable. Okay. So, what do you mean by scalable? We have used the word scaling before. Anyone remembers what is scaling? Yeah, so reducing the bit size, reducing the bit width, okay, bit length or bit width. So, scaling is basically making, I mean in semiconductor or magnetic recording technology, when we talk about scaling, we are talking about reducing the area occupied by one bit. Okay. The area required to store one bit. So, we want to keep reducing, we want to store more bits in a given area. So, when we are talking about scaling, we are talking about reducing the area required for storing one bit of information. So, in semiconductor technology, we talk about the area required in terms of something called f square. Okay. Let us say you have some lithography technology. So, with that lithography technology, you can resolve lines with a resolution, let us say f nanometer. Let us say your lithography technology can achieve 5 nanometer resolution. Okay. So, we call this as f. So, if you remember historically, this used to be this semiconductor technology used to have techniques like 180 nanometer node, 90 nanometer node, 45 nanometer and things like that. Okay. So, now we are in the 7 nanometer node, 5 nanometer node like that. Okay. So, basically these numbers represent the f, which is the minimum feature size we can achieve using lithography, and we express the area occupied by a particular memory cell based on that number. Okay. So, if f is 7 nanometer for example, so f square is 49. So, this whole thing will be 980 nanometer square, okay, something like that. So, if the minimum feature size is 7 nanometer, 20 f square will be 980 nanometer square. So, people do not use 980 nanometer square, but they will use this kind of terminology. Okay, so, the first problem is that this magnetic field switching technology is not scalable. So, you can see from this picture, let us say 20 years ago we were in 1000 nanometer dot. So, your cylinder had a diameter of let us say 1000 nanometer, which will occupy a large area, right. So, you want to move towards say 100 nanometer or 10 nanometer. So, the progress is along this direction. So, you have bigger bit, then you want to make smaller and smaller bits. So, this is the direction of progress. Okay. So, in this image, so the direction of progress is along this line. Okay. So, we are going from 1000 to 100 to 10. This is the direction in which we want to progress. Okay. So, if you look at the current, we need to write information. So, at 1000 nanometer we have like say around 8000 microampere is needed, but if you make the bits smaller, you need more current, say 12,000. If you make the bits even smaller, you need even more current. Okay. So, the current required to write information keeps going up. Okay. So, this is a problem. So, you want to make the devices smaller, but as you make devices smaller, the current you need to write information gets larger and larger. Okay. So, this is the problem. So, that is why it is not scalable. Okay, that is what I mentioned here. And this large current also cannot be supported by transistors. So, as you go from say 45 nanometer technology to say 28 nanometer technology, the current delivered by say a transistor in 45 nanometer will be higher. The current delivered by a transistor in 28 nanometer will be lower. Okay. So, as you go towards better and better technology, the current delivered by transistors is going lower, but current we need for writing information is getting higher and higher. So, we are in a problem. Okay. So, this is not useful. Okay. This is a problem. So, because of this problem, this technology became obsolete. Now, nobody is using this technology. Okay. Okay, let us do some questions now. Wait a minute. Okay, the title does not match. This is the actual question. Okay, the title does not match the question. Okay, most of you are right. So, we preferably we want the MRAM pre-layer to reverse by Stoner-Wohlfarth reversal mechanism. So, all the switching concepts I described, the energy landscape, all of them follow the Stoner-Wohlfarth reversal mechanism. Okay, so, the correct answer is this. Next question. Okay, this question works. This on. It's a bit hot. Maybe switch that on. This one is off. Okay, the total switching current required to switch an MRAM layer of 1000 nanometer was 10 milliampere. So, in the case of field assisted MRAM, if you shrink the MRAM size, the current is supposed to increase. Okay, that is the problem that we learnt. So, it will not be 10 milliampere, it will be a larger value. Okay, so, the correct answer is supposed to be 4. Okay, majority of you are right, but many of you are wrong also. Okay, so, I just described that the problem of field assisted MRAM is if you shrink the MRAM cell size, the current required gets larger. So, instead of 10 milliampere, it should be a larger value. So, the only larger value in this question is 50 milliampere. So, 4 is the correct answer. Okay, this is not working. Okay, this one we have seen. Okay. Okay, so we have almost finished everything. Is it time for break? Okay. Yeah, so we go for a break, then come back by 11:30.